Hey everyone, today we're going to look at a tool called Kisaten. I'm not sure if that's how you pronounce it, but it's a fuzzing tool for Ruby. And this is particularly relevant for protocol parsers, which are parsing untrusted input, because you want to know all the different ways in which they can crash and break, and especially in the case of Falcon Virtual facing the public internet, it needs to be capable of handling different kinds of inputs. Now, I've already done a little bit of fuzzing with protocol HTTP1, which is what you're looking at here. And we're just going to rewrite this from scratch for protocol HTTP2. Now, HTTP1, I think, is a much easier protocol to break because the constraints around the protocol are not that great. Like the ways headers are structured, it's pretty much just anything followed by a colon, followed by anything followed by a carriage return nearline. So the structure of HTTP1 sort of makes it quite easy to fuzz. But I'm not quite sure how we'll get on with HTTP2. But at the very least, it'll be interesting to see. And this particular tool makes it really straightforward, which is pretty interesting. You can pretty much apply this to anything in Ruby and hopefully identify bugs. So let's get started. The first thing I'm going to do is inside my gem, I'm going to make a directory called fuzz. And I might just make it, let's try that fuzz. We're going to fuzz the framer. Framer is the thing which reads and writes the binary HTTP2 frames. And I'm going to steal this baked task. We'll explain that in a minute. It's what runs the actual tool. Right, so there's this tool called AFL, American Fuzzy Lop. I actually don't know what that stands for at all. And what this does is it takes an input directory which lists essentially test cases, like valid test cases, which should parse without error. And then what this tool does is it makes permutations of those test cases and then runs your script against them. And if your script fails, then it's identified a test case which is causing a failure, which may be unexpected. Now, in Ruby, you are protected against the majority of failures, like, for example, seg faults, memory addressing issues, out of bounds errors. All of those become exceptions in Ruby, which is quite trivial to handle, in the design of a server. So I think there's limited use in terms of actually catching faulty input which produces exceptions. But there's definitely cases where if you are going into an infinite loop or some other kind of condition where that logic is definitely going to cause problems. So I think there are some use cases where it's pretty useful. So we're going to go ahead and make an input directory. And this is going to be a little bit tricky for HTTP2 because it's a binary protocol. I'm not quite sure how far we'll get with that, but we'll see what happens. And then we're going to make our script. And the script, this is for HTTP1, so I don't want to just copy this because it's not very instructive. So I'm just going to have a quick look at this, and I think we'll try and build that. Again, I'm just going to chuck that down there, over there. No, down there. Quick reference. Obviously, the details of HTTP1 and HTTP2 are very different. So we're not really in a good position for just copying that code verbatim. It's going to be quite a different structure. Nah, yeah. So we're just going to pull in libproto, which pulls in that stuff, and I think we could probably just pull in the framer, because that pulls in all the frame types that we want. and now what we want to do is we want to create our test code. And what we're going to do is we're going to use the standard in for the test case. So we're going to read from the standard in. Now I believe the framer interface takes a stream and it just does stuff like read and write to the stream. So I believe if we can just pass standard in there, we'll see how we go. Might have to like adapt it slightly, but so make a new framer and it's reading from standard in. And then what we want to do is we want to actually read frames until it's closed. So the framer provides this method read frame. And essentially what it does is it reads the data and returns one of these HTTP2 frames, data frame, headers frame, priority frame, all these different kinds of frame types. And I guess at the framer level, there's no logical relationship between these frames, but a different kind of fuzzing would be fuzzing the connection, which does handle the logical dependencies between frames, like sending continuation frames always have to be sequential. You can't send certain frames if the stream has been closed. There's just like all sorts of things that logic that applies at that high level. So the framer is just the protocol essentially. So let's just start off reading one frame. And this is what I made. I said I wouldn't copy and paste. Let me explain how it works. So there's this underscore parameter, and that's the executable that was used to launch this. And so we're just trying to figure out if we're running inside the fuzzy loop environment. Because if we are, we need to do this special setup. So we require Kisaten, I don't know how to pronounce it at all. And then we're going to go Kisaten.crash at now. What we can do to start with, this means it's going to crash anytime an exception is thrown. This doesn't mean an exception propagates out of the test. It means an exception is thrown. It literally means if your code throws an exception, it will cause it to crash or record it as a crash. So you might have internal exception handling, and this will detect that. And I guess you might find that frustrating if you're trying to actually narrow down on a specific thing. But what you can do is if you start at this point and you catch all exceptions, if you fix the cases that you didn't think about, then you can add a list of exceptions to this list and it will ignore them. It's kind of like an ignoring list. Right, if your test is idempotent, i.e. it doesn't change any kind of global state, and in this case what we're doing is we're creating a new framer and then we're reading a frame. So there's no mutable global state that's changing in here. What you can do is you can put this code in a loop. So we're going to do 10,000 tests. And I actually don't understand fully how this actually works. I assume it's manipulating standard in. And so what this does is instead of like forking your code and running one test per child process, this runs 10,000 tests per child process. So it just minimizes the overhead so your testing will run much faster. But there's another one called like Kisaten.init, which just runs one test and it's kind of not as fast, especially because Ruby has a decent amount of overhead. And finally, there's this else branch, which just runs this directly. And that means once you find a failed test case, you can just run this script and pipe in the failed test case and it will fail without all of this stuff. Because if you try and run it through this, it will just hang because it's kind of expecting to be run inside this AFL test harness. So what we actually need to do now, if we come in here and we just, we actually need to make a valid HTTP2 frame. So let's try and generate some of those. We'll generate a data frame. And so what I might do is let's try and make a bake task to do this. Right, so we're going to make a frame instance. What am I doing? And we're going to write the output to standard out. And then we're going to call out, I think that's the right interface. Let me just double check. Yeah, that looks good to me. And so then what we would want to do is we'll just make a data frame. And I guess what we could do is have like a loop for all of these frame types. But the data frame is one of the simplest ones to create because it's just a length and a bunch of data. So data frame new, we need to pack some data into it. And I think that's just really straightforward. Okay, frame equals new frame pack hello world. I think that will generate a data frame. So let's that looks like it generated a data frame. I need to like hex dump it. Does that look like a data frame? Yeah, I think it is. Is B11? 9. Yeah, B is 11. Yeah. It's because it's 11 bytes of data. Right, so it looks okay. So we've done that. So what we can do is we can stick that into input data.txt. Right, okay, and now this is where the fun happens, depending on your definition of fun. Bundle exec bake run. Oh yeah, so there's a bunch of like stuff I have to do. This tool is a little bit pedantic about having your system set up so that it works efficiently. And actually, you know, fair enough. It does kind of make sense. Wonder if anyone can figure out my password based on how my keyboard sounds. Okay, and there's one more thing I think I have to do, which is this. Apparently my CPU sucks. And fork server failed. Do I need to do that? Now let me just come here. Let's just double check we got a data frame out of that. Okay, we did. That's good. Good sign. Fork server handshake failed. I wonder if this test is no longer working for some reason. Why wouldn't it be working? I had problems with this tool before, and I couldn't, it just seemed to start working completely randomly, but this one is not that different from this one. That's that one. That's that one. Current memory is true. I don't think it's the memory limit. Okay, running with bundler caused problems. Okay, oh, don't run it with bundler. Maybe because maybe I haven't added that to the gem list. Oh yeah, that's okay. Alright, so what you see going on here, normally it tries to point out any issues. So if you see any issues coming up on this page, it will point them out to you. Like issues with the way the test harness is set up, not issues that your code is crashing. That's kind of what you want to figure out. So it's found 12 unique inputs which are causing crashes. So we can have a look at those. So these are variations of the input which are causing crashes. Awesome. That one looks great. And it will literally run. Some people suggested running this for like days, weeks to try and identify issues. To be honest, most of these will just be exceptions. And in Falcon, when an exception propagates up to the accept loop, it just kills the connection. So it doesn't really matter all that much. It's not like a seg fault or something. But obviously, if you found seg faults, that would be a big problem because it indicates a bug in Ruby. So Ruby's already providing a pretty nice environment in which to handle junk input. But let's have a quick look at some of those failure cases because we can have a look at why they're failing, which is, I guess interesting. So we're going to run that, and did I modify that or is it still, yeah, it's still that good. Okay. Put crashes, and let's just have a look at like that one. Oh, hold on, my bad. It's going to be fed in through standard in. So there we go. It failed with invalid frame length, 11 doesn't equal 4. Let's try another one just for fun. It could be nice to actually, could not read frame payload. So a lot of these actually giving me confidence that invalid frame length. This is really good because like these aren't actually errors that I care about because they're checked and they're handled. So what I'm going to chuck that into there because we're just going to ignore that. We don't care about those kinds of errors. So we're going to come back here, kill that, and run it again. And I don't quite understand how it works in terms of persistence because it seems to kill all the data in there, which it doesn't bother me, but I was surprised when I first saw this. I thought, oh, it's going to build up like a list of failure cases. So let's have a look at what those ones are, see if we can find something else interesting. Could not read frame payload. So what that means is the frame length might have been, I don't know, 32 bytes and there was only 10 bytes of data. So, I mean, that's kind of to be expected. Could not read frame header, not enough data. Invalid padding length. That's an interesting one. I'm surprised it's managed to generate that so quickly. So in HTTP2, the data frame can have padding. And I don't fully understand the use of padding. I assume it's something to do with security. Data frames may also contain padding. Padding can be added to data frames to obscure the size of the message. So I guess there's some attacks where if you can, let's say this data frame only contained the user's password, and that went through a compression algorithm which compressed it down to 3 bytes. Then what you can do is if you can generate the same password, you expect it to be compressed to the same 3 bytes. And so if you can recognize that it's kind of leaking information, so maybe that's what this padding is designed to minimize. Falcon doesn't actually use it. Maybe I should just add random pad to stuff, but I don't at the moment. And so what it's actually managed to generate is a test case, which, because padding actually it requires like a special flag to be set. Let me check. There's this flag called padded, which has a value of that 0x8. So that flag has to be set in the frame header. So the frame header looks like that, and that means that somehow AFL fuzz is put 0x8, so set that in that flags, and then that data frame is trying to parse it. Which, it's good, like, it's the whole point. And I guess eventually if you explore every permutation, eventually you'd start generating other kinds of frames, like headers frames and stuff like that. And what's pretty interesting is that there's actually another whole project which could be fuzz, which is protocol HPAC, and we have a bazillion tests. This project literally has this completely sort of inherited like a lot of these. It pulls down this like test case library, which literally has like thousands of tests in it. And what will be really fascinating is to feed that through the fuzzer as a whole bunch of positives and see what negatives you can generate, because we hope this code is correct. It's really critical that it's correct to dealing with requests, because if the headers are decoded incorrectly, with the wrong stuff, or even data could leak between requests, potentially bad. The proxy, Falcon Virtual, talks to the application server using HTTP2, which is using protocol HPAC. And there are probably some class of attack where if you formulate a specific list of headers, because some other client has fed that request through the proxy through the same HTTP2 connection, that has been entered into the dynamic compression table of HPAC, and somehow you could pick, I don't know, like, it's all theoretical, I'm just making stuff up here, but in theory, like, you could probably influence and detect what is already in that dynamic table just based on timing and stuff. So fuzzing this is potentially a good option as well, just to see where it can go wrong if it has any issues. But it has a massive test library. So what's pretty interesting about this is when it crashes, I don't fully understand how it works, but when I was reading the documentation, what it does, I believe, is it actually generates a checksum of your whole program as it's running. And someone could probably correct me if I'm wrong in the comments maybe. But what it does is it uses that to try and determine unique crashes. So what you see over here is it's got 40,000 crashes, but there's only 13 unique sort of paths through your program to generate those crashes. And so those outputs that's stored in that list there, even though we managed to make 43,000 crashes, there was only 13 unique actual progressions through the program. So I think it's a really amazing tool actually to have access to this and to be able to run this against these parsing libraries which are having to deal with real world stuff. And I think the key point is this initial input corpus, if you make this really good, like, put multiple frames and stuff in here, you really start pulling out, things like alignment issues. If you have one of the big problem with HTTP1 is there's no framing at all, or the framing is really, really weak. And one of the attacks which I've seen is having multiple content length headers, and your proxy might use the first one and your web browser might use the second one. And then what you have is like a misalignment of your bodies, like your content that says your body. Essentially what happens is you may end up reading part of someone else's request because the proxy is confused about which content length to use. So the framing of HTTP1 is really not that great. But in theory, HTTP2, you should be able to pick up those issues as well. All the frames have to be valid, and this tool, if you start putting multiple frames as part of the input corpus, it could start picking out some failures there maybe. But yeah, I think Ruby really provides a safe environment for this kind of stuff. Like I said, if you're writing this in C or C++, you'd be expecting to see seg faults. If you had hand-rolled a recursive descent parser or something, and maybe you missed a case or something. But I don't think we're going to see that here, so that's not very exciting. Anyway, that's largely it. It's not really that complicated. It really comes down to having a test function which can read some kind of test case from standard input and do something, and then basically running it in this loop. And so you can apply this to a lot of different kinds of programs. Any program that you can control with something from standard in is a good candidate. And so these protocol ones, which are facing public traffic, obviously the ones that are going to be the most concerning, but there's no reason why you couldn't have another another test in here, which was using, instead of the framer, but the connection, which is the high level object. And then what you could do is you could record valid HTTP2 sessions, and you could build a corpus of that, and then it would make slight variations, like corrupting the packets ever so slightly, and then you'd pick out logic errors, infinite loops, and potentially other issues with this high level code, because this is a much more complicated logic with regards to what you can and can't do in the order of frames and the behavior of the whole connection itself. So yeah, it's not that complicated. I think this is an amazing tool, and if you do if you do have things which are facing the public internet, then this is a great thing to do. And it gives me confidence to run this on this code. I can then go, well, I think Falcon, the chance of having a security issue in Falcon is at least yeah, maybe hopefully reduced by these types of analysis. Anyway, thank you for tuning in. It's really not that complicated, so I think we'll just end it there. But if you have any questions, or I'll commit these to those particular repositories, so you can pull them out and try them out yourselves if you want. Feel free to make some test cases and submit them in pull requests. They'll be awesome. But apart from that, it's not really that complicated. So go forth and fuzz.